This playlist is going to collect together and organize the modules for the probability theory lecture. Now we're just going to cover basic classical probability theory. 5 basic rules together with a simplified version of Bayes' rule. I want to start off by talking about the origins and value of classical probability theory. So where did it come from and why should you study? What's in it for you? Then I want to turn our attention to the formal system. So all of these inference systems that we study in this class have those 3 elements to them. They have a formal system that allows you to explicitly represent, to make explicit those implicit structural elements of the inference or decision problems for the purposes of then taking advantage of that information using the rules for the system. Then we're going to turn to notions of probability theory. So 3 different ways that mathematicians and statisticians and philosophers have understood probability. And we're going to learn that not just to get a better grasp on how people have thought about probability, but because each of those notions actually has cases that it's very apt in assigning probabilities to simple events for, and cases where it's not so good at. So we'll adopt this pragmatic strategy of using the most appropriate notion of probability as our translation heuristic to assign probabilities to simple events. Then we're going to learn our decision procedure. Notice this isn't an effective decision procedure. It's not a mechanical set of rules that if you just follow it, you'll always get an answer and the answer will always be right. You're going to have to think about things. You're going to have to be a little bit more clever using this decision procedure, but it's not particularly overly complicated. There are 5 basic rules together with that simplified version of Bayes' theorem. Now, because there isn't an effective decision procedure, how we translate problems from the real world or from our descriptions that we get in our exercises is going to be very important in helping us to figure out the nature of the event, its underlying structure, and hence how to apply our decision procedure to that event in order to calculate the probabilities in a good and efficient fashion. So let's start with just the first chunk of that whole lecture. We're going to start with the origins and value of classical probability theory. So where did it come from and what's its use? Then we'll turn to articulating the formal system. And specifically, what we're going to talk about is how to represent simple events in the system, how to represent the probability of simple events in the system, how to represent complex events in the system, and how to represent the probabilities of complex events in the system. Then we'll turn to those 3 different notions of probability theory that have emerged over time. And we'll talk about the classical notion of probability, the frequency interpretation of probability, and the subjective interpretation of probability. And as I said, we'll see that each of these interpretations has cases where it's very apt for assigning probabilities to simple events. In other cases where it's more problematic or in some cases maybe even unworkable. And so once we go over those notions of probability, then we'll talk about how we will use them sort of pragmatically, adopting the most appropriate notion in order to assign probabilities to simple events in solving problems. So let's turn our attention now to the origins and the value of classical probability theory. You might just ask, well, what is probability theory? What is probability? All right. This is Girolamo Cardano, and he's going to be our spokesperson for the next couple of slides. We'll see why. And his answer to that is, I'm so glad you're asking me that. For your purposes, it's going to be thought of as the likelihood of something going to happen. But like we're going to see, theorists have 3 different interpretations of the likelihood of something going to happen. So probability is just an estimate, a likelihood that some event will in fact occur. Now, the theory of probability had its origins in games of chance and gambling. And in fact, Girolamo Cardano, who was an Italian physician and mathematician, made a lot of the money to support himself through gambling. And he's thought to have written the first book on probability as a theory about games of chance way back in 1526. However, no one published his book, which was entitled Liber de Ludo Alle, until 1663. And of course, the translation of that title is Book on Games of Chance. Classical probability theory specifically arose in 1654, and it arose as the result of a dispute concerning the division of a stake between two gamblers whose game had been interrupted. A wealthy gambler, the Chevalier de Mere, posed the problem to prominent mathematicians, including a guy named Blaise Pascal, and Blaise Pascal then shared his thoughts in an epistolary exchange. That's not a gunfight, that's an exchange of letters with Pierre de Fermat, who's pictured down here below. And in their exchange, they worked out a lot of the basic mechanics of classical probability theory. This is Christian Huygens, and he was a scientist and mathematician who built upon their work. And in 1657, when I think he was about 28, he wrote a systematic treatise on the classical theory of probability called De Ratio Sinis in Ludo Alle. Sorry, my dyslexia is kicking in. Or On Reasoning in Games of Chance. Now, this work deals with games of chance as well as what was then called the problem of points, which we now know today as expected values. So Huygens wrote this systematic treatment where he took the insights that had been developed by Pascal and de Fermat and came up with a more comprehensive and systematic statement of the view. So it was a very important book. Well, so much for origins, right? Now we kind of have some very sketchy idea where classical probability came from. The next question we want to ask is, what's its value? So you might wonder, why should you learn something devised by late European Renaissance mathematicians and gamblers, primarily for wealthy people and leisure activities? Right? Probability theory, however, is very useful. Probability theory works to compute or to prove the numerical value of the probability of complex events from the probability as the numerical probabilities of simple events. Now, simple events just consist of descriptions of events that are made true or false by one and only one feature of the real world. So, for example, if I roll a die, a single die, a simple event would be it landing with the 6 side up, with 6 dots up. So rolling a 6 on a single roll of a single die, that would be a simple event. One and only one thing would make that event true, and so it is a simple event. What about complex events? Well, complex events consist of descriptions of events that are made true or false in two different kinds of ways, at least for our purposes. So on one hand, we have descriptions of events that are made true or false by the combined truth of two or more simple events, or by the combination of two or more features of a single real-world event. And these are all complex events. So for instance, rolling a 6 on the first roll of a single die and a 3 on the second roll of a single die, that would be a complex event. Two things have to happen to make that complex event true. Our second kind of complex event that's going to interest us consists in descriptions of events that are made true or false in two different ways again. And these are descriptions of events that are made true by two or more versions of the events. And these are also complex events. So for example, rolling a 6 or rolling a 3 on the single roll of a fair die. There are two different ways that event could be true, and hence it is a complex event. Likewise, rolling 2 die with a combined value of 3 is a complex event because there's more than one way to do that. You could roll a 1 and a 2, or you could roll a 2 and a 1. And we'll pick this up and continue talking about the formal system in the next module.